Okay, we're going to take a look at 9 through 14 out of Chapter 4, Section 2. And what they're asking us here is, which of these functions satisfy the hypothesis of the mean value theorem on our given interval, and which don't? And if they don't, why not? Well, what we have to go ahead and take a look at here is, what are the hypotheses that we have? So we need the function to be continuous over the closed interval. And then we also need it to be differentiable on the open interval. So we don't have to worry about the derivative at the endpoints, just the derivative in between them. But we do have to worry about continuity at the endpoints. And they didn't ask us to go ahead and figure out what value or values of C fall on the interval such that it's true. They just want us to make sure that we know whether or not the mean value theorem would apply in the various cases here. So taking a look at number 9. So now, x to the 2/3 power, that is continuous everywhere. Because the denominator is an odd number, we don't have any problem throwing in negatives. We don't have any problem throwing in zeros. So it's continuous everywhere. So it satisfies the first one, but we do have to, so it is continuous everywhere, so it's definitely continuous on this closed interval here. But if we go ahead and take the derivative of it, that's going to be 2/3 x to the negative 1/3. I just want to rewrite this as such. Now we see that we have an issue here. It's not an issue because of the cube root, it's an issue because our variables in the denominator and x equals 0 falls on that interval. And the derivative, so let me move that over. The derivative at 0 does not exist. Hence, this function does not satisfy the hypotheses of the mean value theorem. So if we're going to say no, we have to give a reason. Looking at number 10, we might think that we're in the same scenario here. X to the f of x equals x to the 4/5. It is continuous everywhere. So it's definitely continuous on closed interval 0, 1. And if we take the derivative, That's going to be 4/5 x to the negative 1/5, which is going to be 4 over 5 times the 5th root of x. So we still have a potential issue, but we only need to be differentiable on the open interval. So we would never be called upon to evaluate the derivative at 0 here. So yes, both hypotheses of the mean value theorem are satisfied. And that just goes to show us here how much of a difference open interval versus closed interval can make in a particular question.